let me know if you did not understand the question.
No, I got it.
All right.
So the second option.
No. Do you want some hints or shall I tell the solution? See, I'll
Sorry, sorry. The third option. Sorry.
yes, exactly. That's the right answer. See, the question says that there is a charged particle of mass m and charge q, and this is released from rest. That means its initial velocity is zero, an electric field of constant magnitude, that is E. Alright, now it's asking me the kinetic energy of the particle. So the kinetic energy will be same as the work done by the field on the charge. Alright, so how do we find the work done? First we have to find the force, because work done equals to force into displacement. Now how do we calculate the force? Force on a charge in some electric field E is given as QE. Alright, now we want to find the displacement. How do we find the displacement? We have the force with us, so we can find out the acceleration. As we know, force equals to mass into acceleration. So acceleration will be force upon mass. Force is, as we found out earlier, is QE and upon m. So this is our acceleration. And we have u equals to 0. We have time t. We have to find the displacement. So we can use s equals to ut plus half at square, and u is 0, so s becomes half a and t square. So now we have the force, we have the displacement, so work done will be equal to QE into half QE by m t square. That is q square e square t square upon 2m. That is the C option.
And did by the kinetic energy equation.
Oh, okay. No problem. You can do with that also. But if by chance you do not remember that, then you can also go by the generalized method.
Yes.
All right.
One sec. Can you go back once?
Sure.
Yeah. Thank you.
All right, did you get the answer?
One sec, I'll try.
All right.
Do we have to do by the maximum minimum method or something?
Yes, 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 exactly. You'll have to find the maxima.
So we have to differentiate, right?
Yes. Differentiate and then equate it to 0.
Differentiate with respect to.
With respect to q, because q is the variable here, the small q.
Won't the distance be also variable because we want because we're
No,
checking.
no, see, the distance they have already mentioned, but we have to find the ratio of capital Q and small q, so we do not know the small q over here.
Okay, right. Double differentiation or single?
No, no, only single.
Oh yeah, we already know the max. Yeah. No, sir, could you explain?
Sure. See, we are given a complete charge capital Q, and we have divided this into small q, and the rest is q minus q. Alright, so the force between these two charges can be given as, or suppose the distance between them is r. So the force can be given as k q into q minus q upon r square. And we have to find the maxima of this expression, so we'll differentiate this. So df by dq. So k, k and r square are constants, so we'll just keep them outside. d
Capital K
by
also constant.
is capital K is 1 upon 4 pi epsilon naught.
No, no, capital Q is also constant, right?
Yes, yes, yes. Capital Q is also constant, but in this expression, we have small q also multiplied with it. So we'll just keep it over here.
Isn't capital Q multiplied?
So no, if you open the bracket, it becomes this, right?
No, no, K capital Q because we have the charges as capital Q and capital Q minus small q.
Yes, capital Q is constant.
No, no, outside the bracket.
Outside the bracket, the small q. No, small q is not constant. It is variable.
Yeah, yeah, but that should be capital Q, no, instead of small q because.
No, we have these two separate entities, small q and capital Q minus q.
Oh,
And
right, sorry.
we want to find the force between these two, right?
Yeah, yes.
All right, shall we move forward?
Yes, sir.
All right. So k upon r squared, and differentiating this we have q and minus 2q. Is this clear?
Yes.
And we have to find the maxima, so this will be equated to 0. The constants will be cancelled out. So we have q equals to 2q. All right. And we have to find q upon q, so that is equals to 2. So A will be our answer. Did you understand this? Is there
Yes,
any
sir.
doubt?
No, sir.
All right. Try this question.
Sir, B.
Yes, that's the right answer. See, uh, this one is actually a pretty easy question.
Yeah, yeah,
We
I
have
got it.
been, yeah, uh, let's just see the solution. We have the specific resistance, that is resistivity, as rho. V is given as 3, R is 3, and we have to find length. Alright, so we know that R equals to rho L by A. This 3 equals to rho L upon A. Now we know volume equals to area into length. So A can be written as V upon L. So 3 equals to rho L upon and V and L. So 3 equals to rho L square upon 3. So 9 by rho equals to L square. L equals to 3 upon under root rho. That is the B option. Alright, let's move on to the next question.
VA is equal to VB for sure,
Yes, that's right.
but
See, there is an easy concept which says that the potential decreases as we move in the direction of the field.
okay, yeah, because we are going towards the end.
Yes, exactly. So, with that concept, we can easily
B.
say that yes, B will be the answer. Alright, let's move on to the next.
Minus A comma 0.
Minus A comma
Uh,
0.
which is
No,
C, I guess.
no, that is the wrong answer.
Oh, minimum. Sorry, sorry. That's B.
No,
I
not B
mean,
as well.
I mean A. Sorry.
Yes, is the right answer.
Yeah, yeah,
This is also based on the same concept.
yeah, yeah. Same.
If these are the axes, the electric field is going in this direction, and we have a circle like this. So, in the last point, as much as possible, there will be the
Yeah,
over here, there will be the minimum,
yeah.
and that is A comma 0, which is A. Alright, let's move on to the next one.
Either A or B, I guess. No, it's B, I think.
No, B is the wrong answer. Yes, the right answer will be A.
Yeah.
See, we want to find the work done. So work done can be calculated as F dot S. So F will be field into charge. So in this case, that will be E into Q. So our work done can be written as EQ dot S. In this situation, there is R. Alright, so if we substitute the values for finding the dot product, what do? We multiply the respective coefficients of I caps and J caps. Alright, so in this situation, we will have A and E1 plus B and E2.
Yeah. Right.
Okay.
Not sure, sir.
Alright, no problem. See, what are we given in the question is a ring with some charge distributed over it. Let the charge be lambda. This lambda is the density, lambda charge of lambda per unit length. Alright, and we have to find the potential at the center, that is this point. Radius r is given to us. So what do? We we do not know the potential for this thing. We know the potential only for a small charge. So we take a random portion, a very small portion of length dl. Alright, so what will be the charge on this small dl? It will be lambda dl, right?
Yeah.
And now we can find the potential using this. Small potential dv can be written as k into the complete q upon r. Okay, so we have the potential because of the small charge. Now we want to find the complete for the complete half ring. So we integrate this. So we will get the k and r are constant. So we can take them out. Integral lambda dl. Now this is a definite integration. We will have to put the limits as well for length. So what is the limit for length? It starts from 0. Alright, it starts from 0 and it goes to the half of circumference. So it will be 0 to pi r.
Yeah.
Alright, so in fact the lambda is also constant. We only have to integrate dl, so that becomes L. from 0 to pi r, which is k lambda by r into pi r minus 0. So it becomes k lambda by r upon r, which is simply k lambda pi, which is the option D.
Yeah, sir.
Let me know if you have any other doubts. No doubts?
The formula for potential is K charge upon R, right?
Yes.
Okay. Yeah.
All right, this is the last question for today's session. I'm giving you 2 minutes to solve this one. Shall I give you some hints?
Yeah. And
All right.
force will be 1 upon x, right? Minus 1 upon x. Uh,
Force or the potential are you talking about? We do not have the involvement of force over here.
yeah, the work will be force into displacement. So
No, there is no involvement of work as well. See, we what are we given is field, which is 1 upon x square I cap, and we want to find the potential difference. Potential is integral E dot dx. All right.
yeah.
So this will be 1 upon x square into dx, and putting the limits. See, this is given in centimeters. All right. And the electric field is having the units in meters. So we'll have to convert this. This will be 0.1 to 0.2. Alright, try solving this. I think you can do this now.
Yeah. So C.
Yes, that's the answer. This will become minus 1 by x from point 1 to point 2. So minus 1 upon 0.2 minus 1 upon 0.1, which is minus 5 plus 10 equals to 5 volts. All right, that's all for today. Thank you for joining. Bye bye.
Sir,
Yes.
did you cover the whole chapter?
No, 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 no. We'll be having one more session,
Because
and we'll
there
try
is
to
nothing.
complete it.
Yeah, because there's nothing more scheduled for physics.
As far as I remember, there's one more electrostatics problem solving lecture scheduled for next week.
Yeah, yeah, there's one more. Yes, sir.
All right.
Thank you, sir.
Okay. Bye bye.